Hello, my name is Sarah Gomez. I'm the Associate Director of the Environmental Studies Program, and it is my pleasure to welcome you to the Ho Cunningham Environmental Lectures that, I don't know if you're new to this, we bring every week. So please come back. If you want to receive alerts from these talks, please sign up in the paper sheet that should be passing around. If you are online, we'll put a link in the chat. And we are super thankful to our donors, the Ho Cunningham family, which brings this series every week, but also today's sponsors, which is the Office of Sustainability. And thank you guys for supporting this talk. Most talks are recorded, including this one, so it should be posted online within 24 hours. And before we introduce today's speaker, I wanted to take a moment to see if there are any announcements from the general audience, any events happening, any opportunities, any courses you would like to highlight. Okay, if there is none, then I will turn this over to the Director of the Office of Sustainability, Tina Wilson, who would be introducing today's speaker.
Thank you very much, Coco. So it's my great pleasure as well to be able to introduce my boss, Dano Weisbord. He is, I have to read his title because it's very complicated, the Chief Sustainability Officer, that's not the complicated part, and the Executive Director of Campus Planning. So he helps oversee both sustainability and the planning for the whole university across all of our campuses. So he came to us from Smith about 1.5 years ago. And at Smith, he was their first director of sustainability. And then he became the director for the Center of Environmental, Ecological, and Sustainability. No, there's no design at the end of that right now. Okay. Before that, he advised on corporate environmental responsibility strategy at CLF Ventures here in Boston, where his clients included international mining, energy, and real estate companies. And he organized a regional wind power alliance. He was also the director of Global Associations of Corporate Sustainability Officers in London. He has an MA from Tufts, from our Urban Environmental Policy and Planning Department, and he has a BA in Industrial Design from the Rhode Island School of Design. At Smith, he spearheaded a very similar project to what he's doing at Tufts, where he's electrification and decarbonization of their campus heating and cooling. So it's really exciting to see him here helping us do that same thing. You don't need it.
All right. Can you hear me? Can you hear me at the back, Rocco? Good? Okay. Can I wander around or will I go off camera? Okay. Tina will tell you I'm not good at sitting still, so. Does it? Okay, excellent. All right, let's go backwards. Okay. And also, I just had a piece of pizza, so sorry. Okay. Really, really nice to be here, and I appreciate the invitation from ENVS. I've been coming to a lot of these, and many of them really feature faculty either from Tufts or from elsewhere, and they talk about their scholarship. I'm a little bit different because I'm a little bit more of a practitioner. So taking some really big ideas and thinking about how we apply them into organizations. In our case, this organization, our organization, Tufts University. The process of doing that, of trying to make change, to sort of see a vision through in any organization, it's actually more similar across organizations than different. So I thought for today, I was asked to talk a little bit more about the technical side of this, but this is a pretty diverse audience. And so I'm going to talk a little bit about the technical. I'm going to try and provide some basic information about what this idea of an energy transition means. So if some of it's too basic for some of you, just bear with me. We're just going to keep going. But I also want to talk about not just the technical side, but there's sometimes the things that are most difficult about making change are people and money. So we'll talk about technology and people and money a little bit. So just at the outset, let's just sort of frame the problem that we're trying to solve here a little bit. And I often do this both in historic terms, but also in global terms. So does anybody know, and Eric, you're not allowed to answer this, but does anybody know what this device on the right is? Or have you seen it in person? Anybody seen that? Anybody want to guess? Yeah. It does look like a thing that extracts oil, right? It looks like a pump jack that extracts oil. And actually that thing does go up and down. That's not exactly what it is. Close though. I can tell you this is in London in the Museum of Science and Technology. Nobody? Oh, nobody wants to guess? Somebody online raise their hand? How do I even, do you want to type it into the chat if you're online? Water pump. Yeah, getting closer. This is the oldest example of a Boulton and Watt steam engine. So from the late 1700s. So this is a device, and there was a series of devices, and there was a series of inventors. Watt was one of them. So that when you think about light bulbs and watts, right, that's where the name came from, was from the inventor of a steam engine, right, as a unit of power. This device helped bring in the Industrial Revolution. It helped us convert a natural resource, in this case coal, into work. And it did that much more efficiently at much lower cost than anything we had before that. There was another really important ingredient here, which is the map on the left. Does anybody recognize the location? What's that? Yeah, go ahead. Yeah, it's Britain, right? It's Great Britain. It is England. And this is William Smith's map of the subsurficial geology of Britain. And what he mapped, and for the first time anybody had ever mapped in the world, was where is the coal buried? So if I know where the coal is buried and I can extract it, and then I can use it in a steam engine, I've just created an entire economic system that is cheaper and more productive than anything I had before. Right? And that's the Industrial Revolution. And the Industrial Revolution changed the lives for everybody on the planet. It mostly improved the quality of life for everyone on the planet, but it did so in an extraordinarily inequitable way. Because at the time, the British, who kind of had all the power and the money, right? They were like, we came up with some really good solutions, and we're going to use those to accrue to our benefit, right? So this is what fuels, right, that British colonial empire. And so when we think about this, when we zoom out and think globally, and so I lived from 2010 to 2014, I lived in London, and I was working for an international aid and development organization called ActionAid International. I went to Bangladesh in 2010, and for a climate risk reduction and resiliency conference. And we went out to this location on the left, which is in a place called Shirazganj in Bangladesh. And Bangladesh is a country, it's about the size of the 6 New England states. And it's at the confluence of 2 really big rivers that drain the Himalaya. This is the dry season. In the rainy season, this is all 8 feet underwater because Bangladesh, 70% of the land area goes underwater during the rainy season. So imagine an area the size of New England, but 70% of the land area goes under the water when it rains. The population of Bangladesh is roughly half that of the United States. So I've got half the population of the United States in an area the size of New England, but 70% of that goes underwater. And that's the way it's been forever. And so when you think about what the climate change implications of that are, initially my thought was, well, there's a concern about continued sea level rise. That is a concern, certainly, but the near-term concerns are, in order to live successfully in Bangladesh, you have to grow during the dry season. You have to have all your provisions And when the rains come, the entire economy stops. So you have to have, when the rains come, you have to have enough resource to make it through the rainy season. The problem with climate change in Bangladesh today is the traditional knowledge of when the rains start and when the rains stop has become irrelevant because the rains are starting and stopping at different times. So 1,000 years of traditional knowledge is now less and less valuable. And that is a massive challenge to a lot of very poor people. So that's our global context. So 8 billion people around the planet want a better quality of life. Right now, our dominant paradigm is better is more. I need more stuff to make my life better. I need more water, I need more material. I need more stuff that's made through using devices that emit carbon into the atmosphere. And that's right, that is a cycle that is super dysfunctional for us as a civilization. So that's the problem we're trying to solve, is how do we get out of that? And we have to solve it at every scale. We have to solve it at the household size scale. We have to solve it at the university size, at the scale, at the state scale, at the national scale. Here we are at the university scale. Here's our Tufts, three of our 4 Tufts campuses, right? We have an urban campus, a rural campus, and a, let's call it a semi-urban campus. Quasi, what would we call Medford? I wouldn't call it suburban. I wouldn't call it, anyway, an in-between. We have a lot of different sort of conditions. And we need to think about, well, how do we operate this thing without fossil fuels? And if we look at this and we look at our overall carbon footprint of the university, it looks something like this. This bar here in the middle is our, for those of you who are the carbon accountants in the room, that's our scope 1 and 2 emissions plus some of our scope 3. And you'll see the top of the chart kind of like fades off. That's because we don't know all of our scope 3 emissions. It's something we're working on, but it's actually hard to do. So that sort of fades off, but you can see of the things that we do know, right, most of it is associated with buildings and a little bit of it is associated with vehicles that we own. So as an institution, we need to solve sort of a buildings problem. And so let's talk a little bit about where that carbon is coming from in a minute. This is, I'm going to tell just a couple more quick stories. This is the Board of Trustees of Smith College, where I worked up until a year and a half ago. They are giving themselves a standing ovation when they approved the largest capital project in the college's history to create a new energy system to provide heating and cooling to their entire campus, and to do that through electricity. This is the transition we're talking about, the energy transition, away from combusting things and to using electricity. So we'll talk about that more. This is an awesome moment. This is a career moment when something like that happens. The how you get to that is really complicated. And so when we think about the people and the money and the technology, in some ways, the technology is the easy part. So we'll talk about that, but I just want to focus on the fact that the people are the hard part. Tina mentioned to me the other day that the first Hoku lecture of this semester was focused on storytelling. And so it really inspired me. I just wanted to share a story with you that I used at Smith College a lot because it helped me, right? It's one of the many tools that I use to sort of make organizational change. The woman in the photograph on the left is named Florence Merriam. Florence was a student at Smith College in the late 1800s. And she was from a wealthy family, as all Smith students were in the late 1800s. And she was a member of the then brand new Audubon Society, which at the time was fighting the harvesting of birds for feathers in ladies' hats. And she started an Audubon Society on the Smith College campus. And I've been told, and there's some research on this, that this was the very first example of student environmental activism on a college campus, anywhere. So that's kind of cool. So I use that story at Smith a lot because it's it sort of harkens back to the deep sort of identity of the institution and says, this is something that's been going on here for a long time. Let's think about that. But here's the really interesting thing about Florence. Florence went on to write this book called Birds Through an Opera Class, which is credited as one of the books that changed the practice of ornithology, of science that was conducted using a gun, right? Used to be I'd shoot the bird, then I'd study the bird, to one that was, I could use optics, I could use binoculars, I could use an opera glass. And Florence became the very first woman admitted to the American Ornithological Union. So, right, that's profound impact. And if you are a higher education institution, right, we are all about having our students go out and having profound impact on the world. That is our single biggest contribution to the world. So I would tell this story to say, we've been doing this for a long time. Now I need whatever the Tufts story is, because I haven't been here long enough, but I got to find, so if anybody's out here and knows the Tufts story that I should be using, please come talk to me afterwards, because I need to use the Tufts story. All right, technology, people, money. Keep these three things in mind, because these are the three things that sort of make all of this happen. All right, here's the technology problem. Let's talk a little bit about what the energy transition is. Because right now, when I said, okay, look, all the carbon emissions here on Tufts campus, it's coming from buildings. Well, what is that? And it's really kind of two big things. It's heat and electricity. Okay, there's cooling too, but the cooling I'm making using electricity. So let's just call that electricity, heating and electricity. And there's carbon associated with both of those. From the heating standpoint, I said in Eric's class the other day, like, right, humans, we've evolved a little bit, but like basically, you know, millions of years ago, hundreds, how long ago did humans create fire? Like a long time ago, right? Like our evolution since then is we've taken that fire and we've put it inside of a metal box. Or in the case of an airplane, we've put it into a little round tube. But there's basically, remember, when you're on an airplane, you're never going to fly again. And you're going to hate me for this. But when you're on an airplane, remember, there is an open flame inside that jet engine. It's just fire in a tube. And the same is true of your heating system, your furnace in your house, the boilers here at Smith College. If you look through the big glass window on the central energy plant down the street, it's just that big box. It just has an open flame inside of it. That's how we're making heat. It's a really, really good way to make heat. Lighting things on fire is great for making stuff hot, right? It just has bad side effects. So we have to get away from that. Okay, on the electrical side, where's the carbon in this system is, well, to make electricity, I gotta make things go round and round. And generally, to make things go round and round, I am burning something, turning water into steam. That steam's pushing on a turbine. It's going around and around, and I'm making electricity, right? Electricity is awesome, right? I spin a copper coil against a magnet, and I get an electrical current. You don't need to know any more than that unless you're actually an engineering major. I am not an engineer, and I've made a whole career in energy, and that's all you need to know. I can get electricity from other sources. I know how to do that without carbon. I know how to do that now without coal. I know how to do that without oil or gas. I can do that with wind. I can do that with solar. These are our dominant modes. So if I can imagine a system where my electricity is carbon-free and all I'm using is electricity and I stop lighting things on fire, I've kind of largely decarbonized my system. Airplanes are going to be a problem, just saying. Right? So there's the heat side. The heat side now remains a problem because I've got fire in a box. So how do I make heat? How do I make things warm efficiently with electricity? And that's really the problem that we have. And so let me just talk a little bit about, here's how we heat campus today. And then we'll talk a little bit about how do we do that in the future and how do we take that heat source and how do we electrify that? That's our energy transition. So here's today at Tufts and at a lot of other colleges and universities, we are providing all these services, heating, cooling, electricity in a district system, right? Which means my fire in a box is in the central energy plant, and then I'm conveying that heat out to buildings using something else. In our case, we use steam sometimes. The steam runs through a pipe, or we're using hot water, runs through a pipe from the central plant out to the building. It's not that different than what happens in an individual building where there's a furnace in the basement and the heat comes up through water in a pipe or in a radiator. Similar. But I've got a plant and I've got fossil fuel boilers today. So that's how I make stuff hot. I've got distribution, I'm distributing with steam or hot water, and then in the buildings, I have things like radiators or air handlers, or see these things down here at the bottom, right? This is perimeter heat. That's probably like there's probably a hot water pipe running through that unit, right? And the air flows over it and it makes the room warm. It's doing pretty well today. So that's kind of how we do things today. This is literally choo-choo train technology. Right? We have, it's like, imagine like a steam locomotive. I've got like a big fire and I'm shoveling coal in there and there's like steam and smoke going everywhere. And all of that is like, it's actually representing waste. The heat coming off a steam locomotive, we have the same problem in our district system. We estimate that we're losing about 20% of the energy just in distribution. So I've got fire in a box at the CEP, and that's 80% efficient. And then only 80% of that is getting into this building. That's not an awesome system. That was a great system when coal or oil was really cheap and we didn't care about burning it. So we have some options, right, for decarbonizing a campus. And we could think about, some people talk about offsets, and we could offset all of those carbon emissions, which basically means, we could pay somebody else to reduce their carbon so we don't have to. That is that is not a winning strategy from a global perspective, because we can't all pay somebody else to reduce their emissions. Option 2 is we could use biofuels. A lot of college campuses have used biofuels. I won't name them because I think this is something that sort of has come. It sort of was an idea. Maybe we could burn things that were in the biogenic cycle and maybe there was less carbon emissions. If we burned wood, maybe that was less bad than burning. So that's because that wood, the carbon in that wood was sequestered maybe 50 years ago, whereas the coal, that carbon was sequestered millions of years ago. So maybe it was better to do something in that biogenic cycle rather than extracting it from underground. It is really unclear that there is much benefit in burning biofuels. It's got a lot of problems, and it's been called, the sort of international carbon accounting standard says, well, biofuels, you can count those as zero. But that was a political decision, not a scientific one. So biofuels are really challenging, and probably not burning things is the better solution. Okay, so we're left with option 3, which is electrification. So that's just to give a little bit of background on like, how did we get to that electrification option anyway? So how do we do that? Anybody recognize this device? Yeah, that is a super modern refrigerator. No, that's kind of an old refrigerator. What's a refrigerator do? What? Moves heat. Yeah, where's it moving the heat from? Yeah, it's taking the heat inside the refrigerator and it's putting it outside of the refrigerator. So who here has ever put their hand behind a refrigerator? Yeah, I've seen some nodding heads. Yeah, and what is it? What's it like back there? Hot. Yes, thank you. That's the heat that was inside the refrigerator. So a refrigerator is an electric device that moves heat around. It moves, let's call it thermal energy. Right? I can move the warm thermal energy inside of the refrigerator. I can move it outside the refrigerator. That's pretty cool. Anybody else, like, what's another like everyday object that does this thing? Air conditioner. Who said that? Right there. Okay. Window air conditioner. Right? Window air conditioner, it's moving the heat inside the room and it's pushing it out, or it's taking the cold air out and putting it in. Either way, it's actually doing both at the same time. You could heat your room by turning that window air conditioner around in the window. It's not super efficient, so I don't recommend it, but it is theoretically possible, right? So this device is called a heat pump. And a heat pump is what's at the core of a refrigerator or a window air conditioner in your car, any kind of sort of chilling device, -80 freezers in the laboratory. These are all heat pumps. Okay, so here's a thing, it's been around for a while. That's an electric device that makes things hot and or cold. So let's think about that in my district system sort of provision. So here's my vision for the future, right? Let's start with the plant. Instead of having a fossil fuel powered device, instead of having fire in a box, let's say I have a heat pump. And that heat pump can make stuff warm, and it's really big. And in this case, this is an example. This one on the left is at Carleton College. That's heating their campus, right? So I've got a really big electric device. It's making stuff hot, and then it's distributing that hot medium, right? In this case, it's water, hot water, out to campus to warm stuff up. Your pipes are a little bit different. These are pipes that are being installed at Smith College, right? That's an HDPE pipe with a nice thermal jacket. Instead of losing 20% in distribution, now I'm down to losing, what, 4, 5, 6% in that range. I have my engineering brains back here in the corner. So, right. So now I'm losing less in distribution. And now the challenge is buildings, because what I did here is heat pumps are less good at making steam. It's theoretically possible, but it's really hard. We can use an electric device. It can make things kind of like warm, but not hot. The technology is advancing, but just know that it's like to make things 120 degrees, a heat pump's a really efficient device. To make things 170 degrees, a heat pump is like an efficiency device. To boil water, a heat pump's really not a very efficient device at all at this time. So what I really want to do is say, well, instead of distributing heat to all my buildings as steam, I want to do that as hot water, because that's what my heat pump can do efficiently, cost effectively compared to fossil fuels as well, right? But I have to change what happens in my building. Remember in the first picture, you saw there was a radiator, steam radiator, right? If you imagine you fill up a radiator, it's this big, and you fill it up with steam, right? It's going to warm up the room, right? The air is going to flow over it. And you're going to distribute the heat in that radiator out into the room. If the temperature of my water that I'm distributing around my campus is lower, I need more surface area to get my room warm. So this is an example. This is in the chapel at Carleton College. So they took a really cranky old building. It's not unlike our chapel here. And they put in a different heating end unit so that they could provide lower temperature water to the building, but the room would still get warm. That is an expensive thing to do. So I've got a lower cost to operate, but I've got a expensive to install problem. So just keep that in mind. So that's the future. And it all kind of looks like this, right? This is a conceptual model. And in the case of Carleton and in some of the other places we've looked at, they're using what's called a ground source heat pump system. People call this geothermal, a little bit of a misnomer, right? We're using the constant temperature of the ground to help make the system more efficient. What are you talking about, Dano? Okay, let me go back. Imagine it's a really hot day and you're sitting in this room and it's hot. What's happening? What's the temperature under the ground in the middle of the summer here in Medford? Anybody know? We have geoscientists. 55, thank you. We do have a geoscientist. Right, awesome, right? 55 degrees. 55, we go down 1,000 feet, it maybe creeps up a couple of degrees. But essentially, we have a constant temperature year round. So imagine I push some water down into the ground and my water cools off to 55 and then I bring it up. And imagine that water comes along in a pipe and I bring it into this room and I blow a fan across it. I'm cooling this room. I'm doing that for the price of pumping the water and the energy that's going into the fan. that's actually like a pretty efficient system, right? So on the cooling side, geothermal heat pump is really kind of an awesome thing. On the heating side, it does something similar. So a refrigerator, we would call that an air source heat pump. It's using the air on one side, it's got air on the other side, and it's using the refrigeration cycle, which I will not go into great detail about today. You should definitely read the Wikipedia page. It's awesome about the refrigeration cycle to explain this. But essentially, right, we've got this electric device and we can make things warmer. If it's 0 degrees outside, taking that air and extracting a little bit more heat energy out of it to put it into my building, that's expensive. That takes a lot of energy. But if I took 55-degree water out of the ground and extracted the heat out of that and put it into my room, even though it's 0 degrees outside, that's a lot easier. That's energetically much easier because I don't have quite that huge delta between what my source temperature is and what my destination temperature is. How am I doing, everybody? Is this okay? We're with me? Okay, so that's the benefit of a ground source heat pump system. The other benefit of a ground source heat pump system is there was this little federal bill called the Inflation Reduction Act, which some people may have heard of, and these things get a giant incentive. So, right, and that's entirely about, this is one of the great things. So there's problems with the IRA. There's some really great things about the IRA. One of the really great things about the IRA is that it is really trying to say this electrical transition is really important and we need to use the technologies we have available to us today, which we have, and they're ready to go and they work. And we're gonna make sure that that is on cost parity with other choices you might make, with fossil choices you might make. So you might say, well, what does a well field look like? You're sending all this like water down into the ground and then you're bringing it all back up. And the answer is it looks like this. And in fact, that's the main quad at Carleton College. And there's something like 80 or 100 wells underneath, geothermal wells, 600 feet deep under that grassy spot. So it's disruptive when it happens, but after it's done, you have what you had before. You can put it under parking lots. You can put it under buildings before you build the buildings, right? You can put geothermal wells in a lot of places. All right, so let's look a little more in depth at where we're sitting now. Here's our Tufts Medford Somerville campus. And I made it sound simple, like there's one central energy plant and then like we distribute heat out to all the buildings. And actually it's more complicated than that. So in fact, what happens is these gray buildings are all getting heat from the central energy plant. But like these light pink buildings have their own steam boiler. These light pink buildings have their own boiler. These yellow buildings do and the orange buildings do. So there's actually like 5 separate little mini district systems. And all the red buildings have just standalone systems. Okay, that's just like a lot of different things going on. So we're in a planning process that says like, let's take a look at all of these pieces and let's think about, that's a lot of energy. Like, what's the planning process look like? So step 1 is to say like, well, how much energy is that? How much heating energy? How much cooling energy? I kind of know how much thermal energy, how much heating or cooling I can get out of a geothermal well, but do I have enough space even to be thinking of this as an option? I might not. For example, if you said, hey, Dano, can we just put solar panels everywhere to provide all the electricity to campus? I'd say not on our campus, because this doesn't match up from a scale standpoint, right? You need much more space to make enough electricity for Tufts electrical demand, if you're getting it just from solar. But geothermal, actually, we kind of start to match up. Did you make this, Josh? Yeah, so see, Josh made this chart. So, right, we just sort of said, well, what's the total thermal demand? And like, just conceptually, do we have enough space to drill enough holes to meet that demand? And so the very first planning question was, how much energy? Second planning question was, could I look at geothermal? Is that a sensible solution for our campus? And that second answer is yes. Okay, tick, tick. Now I'm on my way towards electrification. all of the things that I've been talking about, right? I sort of mentioned them earlier. This costs money. The amazing thing is that we're at a moment in time where some of the application of these technologies, because the technologies we have now are kind of choo-choo train technology, because they're inefficient. Ground source heat pumps, the electrification is actually a more cost-efficient way to provide energy services to a campus than traditional fossil fuels. So when people say, oh, well, you know, I don't want to get away from fossil fuels because it's cheaper to operate, that is not true at a district scale. And right, the problem is it does cost a lot to install it. So here I have a conundrum, right? It costs a lot. I need a lot of money right now to save a bunch of money in the future. So if I do all of my planning right, and there's a lot of space between the map I just showed you that says, hey, do we have enough room for geothermal holes, and this chart that I'm showing you today. But if you get all the way through designing that system, you can do something like this. This is a life cycle cost analysis that says, okay, look, here's this dotted line. This is my system that I have today. Here's how much it's costing me. Here's how much it costs me to run it. Here's how much it costs me to repair it, to fix it, to upgrade it. Right? So here's time on the bottom, and here's the cost. That's my dotted line. If I was going to do something different, if I was going to build a ground source heat pump system, what would that cost? Well, let's look at all of the things that go into that. How much does it cost to provide the electricity? How much does it cost in labor? How much does it cost to repair it? My hope is that if we do our planning right, we get a chart that looks like this. This is actually the Smith College chart, not the Tufts chart, because this is done kind of more towards the end. But it says, okay, we're going to look at a 40-year time horizon. Here's my investments. I'm going to build this new system. I've got to spend a lot of money here between now and 2030, right? In Smith's case, it's about $210 million. And then once I get there, here's what happens. This system is suddenly a lot cheaper to operate. And sooner or later, those lines cross. In the case of Smith, it was around 2038. All of this in the future is benefit to the university. That's savings. That's money that we can do. Instead of spending money on fossil fuels, we are now spending that money on other stuff. Stuff for students, stuff for faculty, mission stuff, not operational stuff. So the argument I would make, right, this is why the finance is really important, is to say if you really want to do the things you're good at that we are important to us as an institution, we need to be focused out here, right? A lower carbon, lower cost future, right? Because that's like about making this institution work in the long run. And this is, so when we do our planning well, we end up with something like this. So that's kind of our goal, is to end up with a chart that looks something like this. And there's a lot of things that makes it more expensive or makes it cheaper. So it's as engineers say, it's a real optimization problem, and it's iterative. We keep trying different ideas over and over and over, but then we test them by looking at them through a financial lens. So this is sort of my big point, right? There are certain things that we might do that increase the initial cost, but there's other things that we might do that decrease the operating cost. So the best example of this is if we could circulate water around the campus at 170 degrees, we wouldn't have to spend as much money to convert buildings to be compatible with that system. But it's a more expensive system to operate. So if I could operate the system at 120 degrees, it's going to cost me a lot of money to convert all the buildings, but actually it's going to be really cheap to operate. So how do we make those decisions? Well, that's where that life cycle cost model comes into play. Because maybe it's not 170 or 120, maybe it's 150, maybe it's something in between. And we have to test those ideas. So that's a lot of the planning work. Okay. Let's go back to the people just for a second. We are working right now with an engineering firm called Silas O'Brien. Josh, who's sort of sitting there on the side, is one of our engineers. You should definitely talk to him afterwards. These are some students, some of my students at Smith College. They were working on an engineering capstone class. And they were examining the potential of extracting heat from the sewage system, from the municipal sewage system. This is something I've seen done in Vancouver, Washington. There's a few other cities around the country in the US that have done this, where you basically, instead of using a well to extract heat from, I use the sewage pipe. Why? Because I got a ton of water and it's really warm. And so right, so the heating water and the sewage, they don't ever touch each other, just word to the wise in case you're wondering. But it is a really great source and it's out there running under the streets. So we had these engineering students look at this as a potential project. We did that for a lot of reasons. One of those reasons was because we're actually wanted the answer to that question: was this a viable thing to do? The second was, it's really important for us to make sure that we have students engaged in the problem solving, because when we go to tell our story to the board of directors to say, yeah, we want to spend $210 million. First question the board of directors says is, yeah, but like, shouldn't we be doing something that's more on mission? But if I'm showing them this picture and talking about the work that students are doing, it makes more sense. I'm showing them how it's on mission. I don't have to explain it. This is Rose right here, Rose Sears. Rose graduated in engineering from Smith, and she now is one of Josh's colleagues at Silas O'Brien, so that was cool. And she's working on our project, so that's even cooler. Right, so aligning the mission, just one more example on this front. This is Sally on the right. This is Professor Denise McCann from Smith on the left. Denise is now the associate provost. She's an engineering faculty. She studies dynamic systems control. Sally did her, and Smith students in the engineering program, when they graduate in hard hats. So that's why Sally's wearing a hard hat. Right. These are the kinds of images I use because it reminds everybody, like, what is it that we do here? What we do is we graduate students. We graduate Sally, right? And we want to make Sally effective in the world. Sally did her engineering honors thesis on the role of battery storage in our future electrified district energy system. Would that be an effective way to sort of maintain electrical resiliency? So Sally did that as her honors thesis, and Sally was one of the students who explained the technology to our board of trustees directly. So we had a whole session on the technology with our board, and Sally explained it. That's really good. That's a really good outcome, right? Because then the board really understands, like, hey, I didn't have to tell them, I just showed them. Actually, Sally showed them. They never had a question about whether there was an opportunity cost involved here, because we had the whole thing kind of joined up in the right way. So that's just another example. So here we are. This is, for those of you who don't know, that's our central energy plant, looking very nice at dusk. Architects like these kinds of pictures at dusk with the lights on. We need to be thinking about how we move this transition forward. It is a technical problem, right? It's a financial problem, and mostly it's a human problem. And that human problem, right? And when we scale that, we go back to thinking about what the energy transition means for us as a society. We're going to have to decide. We have to find compelling ways to explain why this is important to people. To change our organizations and the places we work. So I think that's my last slide. I'm just going to check. Yeah. So I think I'm just going to stop there and we'll see what kinds of questions there are.
Thank you so much for that informative overview. Questions? Well, people are thinking, I guess I'll get us started. So you talked a lot about the Medford campus, and here maybe geothermal is an option. I imagine solar may be more of an option for Grafton. Is the Boston campus a lost cause?
The Boston campus is not a lost cause, but it's a really different problem set. So has everybody here have you like at least seen the Boston campus, right? So Boston campus, for those of you who haven't seen it, it's basically 5 really big, high density buildings with no land around them. It is the ultimate urban environment. So we might be able to say, okay, how much energy is used there? Knowable. And then we might say, well, what's the source? What's my future source of energy? Can I use ground source? And the answer there goes, probably not, right? Because I don't have land. So then the first question I asked, Rocco helped me with this. I was like, I'd heard in New York City that there was a developer who used the MTA in New York City was dewatering subway stations. So they were pumping water out of the subway. Maybe we could tap into that and use that as a source. But they're not dewatering the Tufts Orange Line station that's right there at the hospital. So that was a non-starter. I think it's a more complicated question. We don't actually combust fossil fuels on the Boston campus because we're buying steam from a municipal steam utility. The municipal steam utility is combusting fossil fuels in Cambridge and supplying that heat to us in the form of steam. They have a big plan to decarbonize their municipal steam system. It has some real strengths and it has some real weaknesses. And so I think a lot of us are sitting around scratching our heads saying, do we just go with our steam provider and say, yeah, that they're going to solve this problem for us, or do we also need to be taking action? And I think the answer is going to be, we're going to have to do a little bit of both. In Boston, there's also a carbon tax, essentially, on buildings. This is coming to Somerville as well. And so that imposes a cost on us, depending on how much, essentially, carbon emissions we emit in Boston. So that we want to avoid that cost. So that's an incentive. It also turns out for some portion of our energy load, it's probably a lot cheaper to get that from an air source heat pump, which is like a big chiller, than getting it buying steam. So we should be doing all of our efficiency and conservation measures. We should be shifting over some amount of our heating load from steam to air source heat pumps. And then we're gonna like sort of watch the vicinity as the utility provider. We're gonna watch what they do and sort of see how that goes. But we're gonna start putting these things in place. The good news is there's actually really good economic opportunity on the Boston campus. So it's a little bit more complicated. It's not a district intervention. It's much more of like a building by building kind of case by case intervention. It is hard. Grafton, if you've ever been out to the Grafton campus, there's basically from an energetic, when you look at all the energy that's used on the Grafton campus, there's really only one building that uses all the energy, and it's our massive animal hospital. And it's the #2 user of energy across all of our campuses. The #1 user of energy is the dental school, which of course is a 16-story tower. It's a very large building. And it's a clinical space, so there's a lot of fresh air. So the animal hospital really and that's probably a good opportunity for ground source heat exchange. The other interesting thing at Grafton is we do have 2 megawatts for 3.8 megawatts of installed solar. So we have acres and acres of solar panels out there. They've actually saved the university a lot of money over time, and they are a resource, and we need to think about them creatively from an electrical standpoint. That's something that's actually coming back around, and the folks from Silas are going to help us think about that too. So it is different conditions for different campuses. And it may even be that on the Medford campus, it's not the same solution in every part of campus. The Smith College campus, which has about the same number of square feet as the Medford Somerville campus, it actually ended up breaking it into 3 little mini districts. That might be the solution here in Medford. By the end of the semester, I'm going to have a much better, much clearer idea about yeah, we're going to go this way. It's going to be 3 little districts, and it's going to look like that. So stand by. There's one here, and there's one back there, Coco.
Start here.
Okay.
Thanks. Great presentation. Just maybe following up on the last comment you made, bringing it to campus here, you'd shown sort of the moment at Smith when they'd sort of approved this, and then the plan as well. That moment, there's obviously a lot of sort of homework that went behind creating that moment. So in terms of where we are at Tufts, like in terms of what that timeline looks like, or what that sort of, how do you get from this idea where you've got, it's feasible, these many wells you can put in, to the point where there's something to maybe clap about?
Yeah, so that's a great question. I mean, of course, I don't know the answer to that question, but so I will tell you, it took 7 years at Smith to go from like, gosh, actually it took longer than that, right? In 2007, the president said, we're going to be carbon neutral, and nobody knew how we were going to get there. It wasn't until like 2015 that we actually had a technically practicable kind of direction of travel. And then it took until 2022 to get to that moment of everybody applauding. I would like to think that collectively, we're a lot better at this now than we were when I started in 2015. We've got a lot more campuses that have come online. We have a lot better information. We have a lot better examples. And so I'm hoping we can go faster. We also have things like the IRA, right? Which is like, right, there's a bunch of like financial juice in the system that I think should help too. So, like, you're going to hold me to a date. I mean, it would be great if in 3 years we started constructing on a zone, on a location. I think that would be great, right? And that would start, then we'd be on our path to starting taking chunks out of this thing. But don't hold me to that. Everybody online, I don't know. Yeah, Tufts is already 5 years down the road. I just showed up late. So like some of this has been done, right? Tufts also has a carbon neutrality commitment that's 2050. I think our Sustainability Council is having another look at that, because that's the same as the Commonwealth's deadline. So I'm not sure it's not like a leadership position necessarily. Yeah, Eric, but I want to go back here first, if that's okay. Yeah.
Great. Thanks a lot for this presentation. I have 2 questions. I'll try to be brief. The first is, so it sounds like Tufts is doing a lot to move up of combustion by using steam, solar, you said, in one campus. I'm curious if there have been any analysis done to see what's the potential for geothermal, not just ground source, but the even deeper wells.
Oh, yeah.
And I know those have really high upfront costs, but curious if.
Yeah, I mean, we haven't. I will say, so just to give a little context around that question is, if you go down more than the kinds of wells that are used in a ground source heat exchange system like I described, they might be 600 feet, 800 feet, maybe even 1,000. The ground temperature doesn't really change that much in that amount of depth. If I went down a few miles, depending on where I'm located on the Earth's crust, things start to get really hot, right? And if you could tap into the heat of the core of the Earth, essentially, right? That's free heat. That would be cool. And there are certainly places where the heat of the Earth's core is closer to the surface, like Iceland, sometimes uncomfortably close to the surface. Right, so that's a really low cost way to get heat. Here, we'd have to go down really far. So the challenge there is the cost benefit kind of analysis worth it? Cornell University is doing a deep geothermal pilot project where I think they're going down 5,000 feet and looking at whether that's possible. There's a lot of questions I've heard about like hydraulic pressure, like problems around hydraulic pressure. And if you send liquid down, is it like, what's happening? And like, but do you know anything about this, Josh? Have you been following that? They got the permit to start the drilling.
I know something about this too.
Do you know something about it?
BU actually just their book stack looking building that they just built, they have a couple of deep wells, like 4,000 feet. So they do a lot of testing when they install the wells to make sure they're not losing hydraulic pressure, in which case they kind of can't use the well. The other problem with that is how straight, it's very easy, it's relatively easy to drill a hole 500 feet in a straight line. But once you start going 4,000, like one of the wells is on the other side of Commonwealth Ave. I would say that from that building, which is not good. So
Yeah,
there's a lot of, it's tricky.
we had that issue at Smith. Actually, 2 of the wells touched each other in the drilling, even at 800 feet. And then they're both dead. That's bad. You had another question.
Yeah, I hope they're not taking up too much space. Okay. The one other question is, so of course your focus is on the institutional decarbonization of these plants. A lot of us, I'm sure most of us in this room right now live in homes. We may be homeowners or renters with maybe some influence of our landlords. Any advice that you would give on how these same concepts might apply when we're thinking of that next boiler that we need to buy, and what action can we take?
Yes, awesome question. Thank you for asking it. So there's two things you should be thinking about as a homeowner or even as a tenant that you should be trying to work with your landlord on. One is if your boiler dies, or if you're time to replace your boiler, you can get an air source heat pump, which at a residential scale works pretty well. And if you look at some of our new buildings, like over on Winthrop Street, there's some new buildings we just built. They're 100% electric. They're using air source heat pumps. The Commonwealth is offering like $10,000 of incentive for every one of these air source heat pumps. It's actually right now is the time. Anybody who has a boiler, if you want to replace to an air source heat pump, there is tons of state money, and you should go get it. So that's thought one. Thought two is there is a larger movement in the state, and I would encourage everybody to take a look at an organization called HEAT, H-E-E-T. They are advocating for district scale solutions for homeowners and neighborhoods and communities. And I think this is where we get into like really starting to think about like, how do we like, this is like there's an equitable energy transition question here, and HEAT is doing a lot of work. So I encourage people to like they have like a map that says, like you can go sign in and say, I'm a homeowner and I want district geothermal in my neighborhood, and here's where I live. I would encourage you to go put a pin on their map, because they're doing really effective advocacy. So, right, this is about like sort of acting in your own home scale, but also doing that, finding those organizations and doing that advocacy. So thank you. Eric, did you have a question? Are you running away now?
Getting this done is directly proportional to the number of people on campus talking about this and understanding it and getting excited about it. So I'm just going to say that. And Tufts has done this kind of thing before in terms of campus-wide educational initiatives. So I think everybody in this room can play a role. It's fantastic. Can you repeat that for people online?
Yes, I mean, I will attempt to. So Eric's point was that the speed at which we might get this done is directly proportional to the extent to which our community advocates for it, in short. Did I cover it, Colin? Okay, excellent.
Thank you so much for a great talk. I was wondering, are the heat pumps easily accessible to new buildings that are being created, especially as Tufts grows, as our population grows? How are you mentioned that new buildings are like 100% electrified, and how does a heat pump play into this?
That's a great question. It's so much easier to do this with new construction. So when we look at the JCC, inside the JCC, the water that's heating that building is being circulated at 120 degrees. So that building is like just plug and play. I don't have to do anything to that building, and I can use whatever heat pump we throw at it. So that's like so new construction is great, right? But of course, our existing community is like a mix of new and old, and the old things are a real challenge. And so finding ways through that are economic for old buildings is really important. And that's where some of these like neighborhood and district heat pumping solutions might become really helpful. There's a pilot of one of these projects out in Framingham in Massachusetts, where they've gone to a community-wide district system. Yeah, Colin.
I loved your borehole map. I'm super excited to see those holes go in the ground. One of the things that's always struck me about Tufts is how much it floods on top of the hill.
Mm-hmm.
And so just being on top of the hill, it doesn't seem like it's a major barrier to doing this in any part of the campus. And I was just wondering if you could talk a little bit about what you've learned about what it matters where you are on campus in terms of tops of hills, bottoms of hills. The fields obviously are low lying.
Yeah.
You know, so does it matter? Like, what have you found by sort of analyzing the data from Grant Garvin?
So it does matter and it doesn't matter. Here's the challenge. Big picture, wherever we drill a hole kind of on campus, kind of the thermal yield is more or less the same. It's not going to change that much. it's easier to go someplace just to mobilize to like from a constructability standpoint, it's easier to go to someplace like the big athletic fields because the problem with our quad, unlike Carlton's, is it's just covered with hidden infrastructure. There's electrical lines and communication lines and gas lines and all kinds of stuff under there. It makes it just makes it very hard to drill it. So I doubt there will ever be a bore field on the academic quad just because it's too chopped up by other stuff. Also, like we get into trees and like it's like we want to stay away from the trees probably. That's like counterproductive. So those are the kinds of things that go into this. What Grant, who's a former geoscience faculty member here at Tufts, we've drilled about 60 holes on our campus, which is amazing, from 12 feet deep to 2,000 feet deep. And we have a lot of geophysical data about what the characteristic of those holes is. All that was given to our engineers who are sort of went into that calculation of how many holes would we need at what depth. But more likely it's going to be, the bigger problem is the constructability than kind of the specifics of the geology.
So we're at time, but I would like to ask you to conclude, given your wealth of experience and something you said that, I mean, you work in energy and you don't have an engineering background. And given the fact that we have a lot of early career people in the room, can you give some advice on how to get to a position like you have right now?
Oh, okay. Yeah, let's think about this really quickly. Okay, so first of all, everybody, I went to design school. I have a Bachelor of Fine Arts. And then I spent 7 years wandering the wilderness. And then I came to Tufts for graduate school. And I'm not making this up. I know I sound like a shill, but actually like I went to UEP and that was life-changing. So that was a good thing. Don't rush into grad school, figure out what you want to do, get some experience, and then like, right? And just like allow it to unfold. Talking to people is really, really valuable. So, and you're just, even if it's not, you feel like maybe it's not moving things forward, you're building social capital that will help you throughout your career. So those are a couple thoughts. Thanks for that, Coco.
Great advice.
Yeah.
All right, well, thank you, Dano, one more time. And I see you everyone as next week.